Hello, everyone. My name is Theodoros Papanikolaou, and I'm a postdoctoral researcher at Scuola Superiore Meridionale di Napoli, in Italy. First of all, I want to thank the organizers of the Early Universe from Home for giving me the opportunity to talk to you today about my work. So, as you can see from the title of the talk, we will discuss today how one can constrain non-Gaussianities with primordial black hole-induced gravitational waves. So let me start with a brief introduction on primordial black holes, which from now on I will call them PBHs. PBHs form in the early universe typically out of the collapse of enhanced energy density perturbations. And this happens basically when the energy density contrast of the collapsing overdensity region becomes greater than a critical threshold value, which in general depends on the equation of state of the universe at the time of PBH formation. At the end, one is met with the formation of a black hole with a mass of the order of the cosmological horizon mass at the time of formation being inversely proportional with the Hubble parameter. Thus, the earlier a black hole form, the lighter it is. This gives us an opportunity to probe a wide range of masses being associated with a very rich phenomenology, as you can see here from the schematic figure. Typical black hole masses forming nearly after the end of inflation are of the order of 10 to 5 grams, very tiny, whereas black hole forming during the Big Bang nucleosynthesis era, they are supermassive, with their masses being of the order of millions of solar masses, potentially constituting good candidates for the seeds of large-scale structures of our universe. Interestingly enough, within the asteroid mass window, where we do not have observational constraints for the abundances of these black holes, according to recent arguments, these black holes can constitute viable candidates for dark matter. So, giving us an overall view and the motivation behind primordial black hole physics, let us focus now on a particular mass range, namely the ultralight primordial black holes with masses below 10 to 9 grams, which evaporate before Big Bang nucleosynthesis. If you account for the cosmic expansion and extract the abundance of these black holes, you will see that grows linearly with a scale factor. Thus, even if we start with a tiny amount of for their abundance initially when they form, these black holes can later dominate the energy budget of the universe. And this should happen before Big Bang nucleosynthesis, so as not to disturb the production of light elements happening during this era. This is why we have said here this upper bound is we required to evaporate before BBN. Interestingly enough, as we will see in the following parts of the talk, during these early matter-dominated eras, one can produce an abundant production, can produce abundantly gravitational waves induced by primordial black hole energy density perturbations. Let us see then in more details how one can connect primordial black holes and induce gravitational waves. In particular, if you go to the cubic order perturbed gravitational Lagrangian, you will see a coupling of the scalar metric perturbations phi with the tensor perturbations h. So whenever phi is enhanced and leads to the collapse and the formation of a black hole, it can induce through this coupling tensor modes translated to gravitational waves. After a lengthy calculation, one can extract the tensor power spectrum, which can be recast as a convolution integral of the power spectrum of the gravitational potential phi, a la Bardeen. So with this kernel function being a function dependent on the thermal history of the universe at the time of the gravitational wave production. At the end, one can define the gravitational wave spectral abundance being proportional to the tensor power spectrum Ph. Let us see now, before going to the technical parts of the talk, the phenomenology associated to these PBH dominated eras before BBN. First of all, through the evaporation of these ultralight black holes, one can actually drive reheating, since during this process we can produce democratically all the standard model particles. In addition, we can inject to the primordial plasma potential dark radiation degrees of freedom, increasing the effective number of relativistic species in the early universe, and in this way alleviating naturally the Hubble tension. Then, one, through the evaporation of these objects, can actually produce uh, products of Hawking evaporation, which actually decay through processes out of equilibrium, violating the CP symmetry, producing in this way the baryon asymmetry in the universe. Finally, one can produce gravitational waves induced by primordial black hole energy density perturbations, which, according to recent works, are in quite good arguments with the recently released GW data in the nano-frequency range, nanohertz frequency range by pulsar timing arrays. So, having said that, regarding the phenomenology of the PBH-dominated era, let us now go into the details to the technical part of the talk. So, imagine that we have a population of primordial black holes randomly distributed in space, and which, for simplicity, they all have the same mass. So under this assumption, one can work out the power spectrum of the PBH matter field being dependent on the PBH mean separation scale rho bar, which is, it is associated, as you can see here, with an effective UV cutoff scale, below which we go to the nonlinear regime breaking perturbation theory. Since now we have a two-component system, a matter in form of black holes and radiation, one can define an isocurvature perturbation in this way, and accounting for energy density conservation and the fact that black holes initially are subdominant compared to the radiation background, one can straightforwardly show that the initial isocurvature mode at formation is almost equal to the energy density contrast of the primordial black holes, which behave in this way as an isocurvature mode. This mode, later on, when the black holes will dominate, will convert to a curvature perturbation associated to, to a gravitational potential a la Bardeen phi. So what we did, we treated separately super and subhorizon scales, extracted at the end the power spectrum of this gravitational potential, which can be recast in this way, where we see here the appearance of three characteristic scales, namely the UV cutoff we introduced before, and the KD and KFAB scales, which are the scales crossing the cosmological horizon at the onset and at the end of the PBH-dominated era. Let us also comment on this K-cube factor, which comes from the Poisson statistics of our gas, and the suppression factor here, which depends on the ratio of K over KVAP, which is present here since scales with the time variation greater than the PBH evaporation time are effectively suppressed due to the non-zero pressure of the radiation fluid. So having this power spectrum for phi, one can compute the tensor, the induced gravitational wave spectrum, as we mentioned before, using these formulas. So here we show the induced gravitational wave signal today as a function of the frequency for some fiducial values of the free parameters of our setup, which is the mass of the black holes and their initial abundance of formation. So as you can see, it can be well within the frequency detection bands of gravitational wave observatories. So up to now, we have assumed that we have a gas of randomly distributed primordial black holes. This is actually come from the fact that we have assumed that these black holes form out of the collapse of enhanced Gaussian primordial curvature perturbations. Let us now relax this assumption and see what will be the effect of non-Gaussianities. So in order to have some quantitative results, we will work with local time non-Gaussianities, which are actually described through the nonlinear parameters FNL, GNL, and tau NL, which actually quantify the relative amplitude of the bispectrum and the trispectrum compared to the power spectrum, PR, of the curvature perturbations. So at the end, using a path integral approach, one can compute the correlation, the two-point correlation function of our PBH matter field, which is actually the integral of the power spectrum PBH in the Fourier space. At the end, working in the superhorizon regime and smoothing our density field on scale smaller than the horizon scale at PBH formation, one can recast the power spectrum for delta PBH as a sum of a k-cube term due to the Poissonian, which is actually the Poisson term, plus a non-Gaussian term, which is proportional to the primordial curvature power spectrum times a quantity which depends on the trispectrum parameter tau and L, and with this term actually being responsible for primordial black hole clustering. To be more compact, one can define an effective tau and L in this way and write the power spectrum for the PBH gravitational potential as the sum of a Poisson and the non-Gaussian term. Let us now plot this P phi to see how it looks like. So to do so, we should make some ansatz regarding our primordial curvature power spectrum, which we assume that it's scale invariant on large CMB scales and has a log normal distribution around the PBH formation scale. Regarding tau and L, inspired by scale-independent F and L parameter, one can parameterize it phenomenologically with a cyclic normal distribution which peaks at the PBH formation scale. So with these ansatz, and by fixing to some fiducial values or free parameters at hand, one can see here P phi as a function of k, where clearly we can see that on small scales we are dominated by the Poisson term, whereas on large scales we are dominated by the non-Gaussian clustering term, which depends on tau and L. One can also make a study regarding the order of magnitude of the characteristic scales of the problem shown here in the vertical dashed lines. In particular, one can show that all of these scales, depending on the value of the mass of the black holes considered in their initial abundance, are always larger than 10 to 5 megaparsec minus 1. So with these actually portal, one can probe in very small scales, otherwise unconstrained with typical CMB and LSS probes. One can then plug in this power spectrum to our formula for the induced gravitational waves and extract again the gravitational wave signal today, which apart from the high frequency peak, due to the Poisson term seen here, we have as well a secondary peak, which peaks at lower frequencies and depends on the trispectral parameter tau and L. We also extracted an analytic approximation for this signal, which can be seen here as a function of the different parameters at hand. Finally, by saturating our gravitational wave amplitude at the two peaks to the upper bound on the gravitational wave amplitude from BBN and from LVK collaboration, we extract the upper bound constraints on the joint parameter tau and L bar PR as a function of the mass of the black hole and their initial abundance. Here we see in the color axis these upper bound constraints or our joint parameter. The lower gray region actually is not of interest since there we don't have PBH dominated eras, and the upper gray one is excluded since there we overproduce gravitational waves. We also plot in the dashed red curves the iso-KF contours. Finally, let me conclude. We studied today the gravitational wave signal induced by PBHs number density perturbations abundantly produced during early matter eras before BBN, driven by ultralight primordial black holes, and which can be actually detectable by gravitational wave observatories. We also include into our analysis the effect of primordial non-Gaussianities on PBH clustering, finding at the end a gravitational wave signal which has a secondary peak at low frequencies dependent on the trispectrum parameter tau and L. by saturating our gravitational wave amplitude at the two peaks of our gravitational wave signal. At the upper bound we have from BBN and from LVK, we set constraints on primordial non-Gaussianities on very small scales, which are otherwise unconstrained by current CMB and LSS probes. Finally, I think I convinced you that the PBH induced gravitational wave signal can serve as a new messenger from the early universe. Thank you very much for your attention.